Now, let me think about the rotor inversion symmetry. Now, this is rotation and invert. This is what we call rotor inversion. For instance, one-fold rotor inversion, one bar, is the same as inversion center in here. And now this is right-hand operation here. Now you rotate 360 degree and invert. So this right hand one goes to the left hand in here. This is what we call one bar, or we can call it inversion center. For the stereotype projection, now if you have upper pole, right hand in here, then now you rotate 360 degree, the same position, right hand. Now you invert it. You invert it, then it goes to the left hand. This is minus pole, down pole. In the stereotype projection, we're drawing the spheres like this. Then this is the upper pole. You invert it. Now this is the other side of the hemisphere. So this is now the down pole. And at the same time, you invert it. So the right hand goes to the left hand operations. So it's incongruent operations. Two bar is 180 degree rotation and inversion. Okay, so if I have one pole right hand in here, I have 180 degree operation and inversion it. Okay, so this is where the lattice point locates. This is two bar, two-fold, and inversion. Okay, so this is left hand. In the stereotype projection, if you draw these stereograms, you find out that this one and this one is in the same position, but one is in the upper pole. That's right hand. Now the down pole, that's left hand. Incongruent operation. That's two bar. This is stereotype projection of two bar, two-fold rotor inversion. Now, when you do this operation, you have to do it up until you go to the original position. So down pole, again, 180 degree rotation, then inversion, that it goes to the original position. So there's only two poles in there. So one pole generates not only one extra poles. Now let's do it 3 bar. 3 bar is, for instance, if I have one pole, right hand, upper, now 120 degree rotation inversion makes left hand down pole. Okay, now 120 degree down pole, left hand inversion. So it makes upper pole, right hand. Okay, still it does not go to the original position, so I have to do it continuously. So 120 degree rotation inversion, it makes in here. So 120 degree rotation inversion, down pole, inversion, upper pole. Now it makes 120 degree inversion, 120 degree inversion up until you go to the original positions. So this is 3 bar. So there is 3 poles in the upper hemisphere, and there is 3 poles in the down hemisphere, and upper pole is all right hand, and down pole is all left hand. This is what we call inversion triad 3 bar. Okay. Now this is, I'm sorry, so this is 4-fold rotation inversion. Okay. So if I have one pole on the upper pole, right hand, follow me, 90 degree rotation inversion. This is the second pole generated. That's down pole because it's inverted, and this is left pole. Again, down pole, left inversion. So it's upper pole, this is right hand. Again, 90 degree rotation inversion, down pole, left hand. 90 degree rotation inversion, it comes to the original position. So now all the symmetry operation is done. So there are two poles in the upper position with right hand. There are 2 poles which has 90 degree angle separations which is down pole, they are all left hand. So that's 4 bar. Now 6 bar, let me do this. I have the here, but let me do the 6 bar rotor inversion operations in here. If I have one pole, upper pole in here, 60-degree rotation, inversion, so it makes down pole in here, right? And now 60-degree rotation, inversion, upper pole. Now 60-degree rotation, inversion, down pole. 60-degree rotation, inversion, upper pole. 60-degree rotation, inversion, down pole. So there are 3 poles in the northern hemisphere with the right hand. Now there are the same 3 poles in the south hemisphere with the left hand. So this one has upper pole and down pole in the same stereopic projection, but one is upper pole, one is down pole. All the upper pole is right hand and all the down pole is left hand, because this is generated by rotation and inversion symmetry elements. Now, so far I described only one rotation axis. But as we know, the crystal structure is built up in 3-dimensional space, so there are 3 different axes. So I have to discuss about the rotation axis of each axis. And each axis can have 2-fold, 3-fold, 4-fold, 6-fold. Now, when there are multi-rotation axes, which should be in crystal structures, and what kinds of symmetry elements can be possible? That's something that I would like to discuss. But this is a little bit complicated. The geometry is quite complicated. But basically what I wanted to tell you is when there is a lattice point in the center of the sphere, and when you have one rotation axis, when you have another rotation axis, if you have one rotation axis operation of one pole, which is on the surface of the sphere and rotate by alpha angle, and if I have this B rotation axis of beta angles, then this second pole is going to number 3 poles by the successive operation of A and B. Okay? In this case, this third pole should be the same with the certain rotation axis with certain rotation angles, so that this any 2 successive operation should be matched by the third operation. Okay? This is a little bit complicated, and the geometry-wise, there is a Euler constructions, which is all drawn on the surface of the sphere, and this is quite complicated. And of course, if you want to go in detail, then we can derive all these equations, and then we can find out what kinds of symmetry elements can be possible for each 3 rotation axes. Okay, it's quite complicated. I don't want to go in detail in here, but basically, let me tell you that when there are multi-rotation axes, any 2 rotation axes, any 2 rotation operation should be matched by the third one. So when you have 3 rotation symmetry elements, all these each rotation axis is not mutually independent each other. Any 2 operation should be matched by the third operation. So there is severe limitations of what kinds of multi-rotational symmetry the crystal structure has. It's basically, there is Euler constructions, there's a complicated geometries, but you have to think about that just the 3 rotation axis is not mutually independent to each other. Any 2 operation should be matched with the third operation. Otherwise, this 1 operation, 2 operation can generate another poles by the third operation. Then this another poles should be generated by the another poles by the first, second, etc., etc. So all the surface of the sphere can be, of the poles, is just defined by all the poles in there. So it's not well matched. So there's a severe limitations for that. In this case, if you calculate these Euler theorems, Euler constructions, there's only these symmetry elements which is possible. One is 2, 2, 2, which means that 3 axes all has twofold symmetry. And at the same time, these axes should be perpendicular each other. X-axis, Y-axis, and Z-axis should be perpendicular each other. This is the only case where it can match. All right, let me go the stereopy projection of this operation. In order to explain this, I described about stereopy projection, how you utilize your Wolfnets to rotate certain poles by the certain rotation axis. If you followed that, then I hope you can follow me. Let's do the stereopy projection operation of this 2, 2, 2. Okay. This is stereopy projection. I know that this x-axis has twofold. X-axis has twofold. This y-axis has twofold. So x is penetrated, so there's twofold symmetry in here. Now g-axis has also the twofold, and this one should be perpendicular each other. So this is the symmetry elements of the 2, 2, 2 in stereographic projection. Now if I have one pole in here, now I rotate it by the g-axis by twofold rotation operation. Then in the Wolfnet, you draw it, small circles, and the pole should go there, 180-degree rotation operation. That's a g-axis operation. Okay. Now let me do the x-axis operation. X-axis is now in the plane of stereographic projection. So in the Wolfnet, you draw your rotation axis in the north and south, and it follows on the small circles in the Wolfnet, and you do it 180-degree rotation. If you do it, it goes to the down pole, and it goes to the down pole like this. Okay? Can you follow me? So far, what I did is a g-axis operation and x-axis operation. I didn't do any y-axis operation. Okay? But if you're looking at this y-axis operation, you know that this y-axis operation is already satisfied in here. Oh, the third axis should be there as perpendicular to x-axis and y-axis, and it should have twofold rotational symmetry. It's just there. It does not generate any new poles. By just two rotation operation, the third operation can be there. It does not generate any new poles. Okay? So this is what I meant, that for the multi-rotation axis, the 3 axis should be defined with certain symmetries. Okay, now there is a 2, 2, 3 rotation operation. 2, 2, 3 is defined like this. This is g-axis as threefold, z-axis as threefold. Now there is a axis with twofold, and twofold, 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 twofold. If you define one axis here, there is a threefold rotation in here. Threefold means that by rotating about 120 degrees, the same thing should be there. That's the symmetry. So if I put x number in here, then this is the x, and again, this is the x, which is generated by the threefold operation. So this is one twofold. Okay. Now, in between these twofold, there is a y-axis, which is also twofold. So this is 3, 2, 2, or what we call 2, 2, 3. But in the symmetry-wise, in the axis-wise, this x-axis and y-axis is basically the same thing, because this is just axis. So sometimes we don't define this y-axis, we just write down 3, 2, with just blank in here. Okay, because the axis as the straight lines, it penetrates. In this arrangement, x-axis and y-axis is the same thing, so we don't have to define the third two-fold symmetry elements in here. Now if I draw any poles, then general pole here, 3 folds generated by the 3-fold. For each 2-fold, it generates another 2-fold, 2-fold, 2-fold. Again, I'm doing g-axis operation and set over x-axis operation. It generates 6 poles. This is all rotation, so everything is in the right hand. It's just the upper pole and down pole is different in here. And it generates 6 poles. And now if you do it, again, you will see the y-axis operation is already maintained. It's already in there. It does not generate new poles. Okay, so these 2, 2, 3 symmetry elements is possible. Now 2, 2, 4, 2, 2, 4. This is quite complicated. Become complicated. Now this is 4-fold. I draw 2-fold. This is x-axis. Now this is x-axis. Symmetry-wise, the same x-axis. Symmetry-wise, if I write down x, this is x, and this is x, this is x, because this is all generated by the 4-fold symmetry. Okay? Then in between these 2-fold, I generate another poles, which is what we call y-axis. And all the y-axis is the same thing because the 4-fold rotational symmetry generates 4 same symmetry elements in there. Okay, so this is 2-fold, 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 2-fold. Now if I put any poles in here, then 4-fold is generated in here. Now 2-fold generates here. I only do the 2-fold set over x-axis operation. I didn't do any y-axis operation again. But you know that this y-axis again has the 2-fold rotational symmetry, automatically matches. Okay, so this is 2, 2, 4. I don't want to draw 2, 2, 6. Again, the g-axis is 6-fold. Now you can have perpendicular 2-folds. Basically the symmetry-wise, and let me just draw the symmetry elements in here. This is 6-fold. Now you draw 2-fold. Then there is the 6 2-folds in here. It's all generated by 6-fold rotation. Now I draw another 2-fold in between these 2-folds. So if I generate any poles, then again, 6 poles, 6 poles, so 60-degree rotation, 60-degree rotation, 60-degree rotation, and 2-fold, 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 2-fold. Am I right? 2-fold, sorry, something wrong. 2-fold and 2-fold. So it generates 12. Yep, 2-fold, 2-fold in here. So 12 poles. That's what we call 6-2-2 rotational elements. Now in this multi-rotation axis, there are 2 more multi-rotational symmetry that is available. This is what we call cubic symmetry. This is quite complicated. And this one basically shows that 2, 3, 3, meaning that all the x-axis, y-axis, g-axis, 100 type of axis in cubic crystal structures has 2-fold, and all the 111 axis, now having 3-fold symmetries. Okay, this 3-fold generates 2 111 axis, and another 3-fold generates another 2 3-fold rotation axis. So this is 2, 3, 3 that is available in multi-rotational systems in cubic crystal structures. The most complicated one is this one, has 2, 3, 4, or we call it 4, 3, 2. Although 100 type of axis has 4-fold rotational symmetry, now all the 111 axis has 3-fold rotational symmetry. Now all the 110 axis has 2-fold rotational symmetry. That's what we call 4, 3, 2. I don't have enough space to draw the diagram in here, but let me draw two cubic crystal symmetry elements in here. Let me first draw 2, 3, 3. People write it 2, 3, which is all the 1, 0, 0, all the 1, 1, 1. Okay, in the cubic systems. Then in the stereopy projection, if you follow the crystallography stereopy projection of the cubic standard projection, then you can find out what I'm drawing in here. So this is the g-axis has twofold, and x-axis has twofold, y-axis has twofold. So this is all the 1, 0, 0 type of planes, poles, has twofold symmetry. And all the 1, 1, 1 poles has now threefold symmetry in here. Threefold, 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 threefold. Okay, this is stereographic projection of the 2, 3, 3 multi-rotation systems, which people also write it as 2, 3. In this case, the 2, first digit, meaning that all the 1, 0, 0 type of direction has twofold symmetry, and all the 1, 1, 1 axis has threefold symmetry. Now, if I draw the poles, let me say that if I have any general pole in here, now the g-axis generates this pole, twofold. Now this x-axis, this 1, 0, 0 axis generates down pole here, then it generates down pole here. Okay, this 0, 1, 0 axis operation, twofold rotation operation, you don't have to do it. It's already satisfied. Now, if I do the threefold rotation axis, this is threefold rotation, which is 1, 1, 1 axis, which is inclined rotation axis. So when you do the Wolfnet operation, then you put it, this 1, 1 axis in the east and west, and put this 1, 1 axis on the center, and make it vertical, and then move it and rotate by 120 degrees. Then you go back to original positions. Then that's how you find out your poles, where your pole locates. But basically, this is the simple. This is, if you think about here, this is 60 degree, 120 degree. The poles are generated here. And so this is 60 poles are generated here. Okay, this is threefold rotation operation of this pole along this 1, 1, 1 axis. By the same token, here poles generate here. This is threefold rotation operation of this pole. Again, this is twofold. This is down pole. This is down pole, and this is the down pole. And this is the down pole, and then, yes, these three poles are generated by these threefold rotation operations. So in this case, 12 is multiplication of this symmetry. All right, the final complicated one is 4, 3, 2. This is again cubic multi-rotation symmetry that is available. Now this is all 1, 0, 0 type. This is 1, 1, 1 type, and this is 1, 1, 0 type. Okay, symmetry in the stereopy projection. Again, this is the cubic systems. So you know how to draw this stereopy projection of the cubic crystal systems. And this one has fourfold, this one has fourfold, this one has fourfold. Okay, this one has fourfold. Now this one has threefold, 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 threefold. Now 1, 1, 0 type of poles or directions has now twofold. So this one has twofold, this one has twofold, this one has twofold, twofold, this one twofold, 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 twofold. Okay, so this is 432 multi-rotation axis where the symmetry element is represented in the stereoscopic projection. Now, you have to find out how many poles are generated in this symmetry. What is the multiplication factors? Okay, it's not easy, but let's just do it one by one. This is quite complicated. For instance, if I have any poles in here, then this fourfold rotation generates 4 folds in here, 4 folds in here, and 4 folds in here. This is just the g-axis operation. Now, if I do x-axis 1, 0, 0 operation, then this is the small circle, then this is the small circle that you put it, your wolfnet. Now this rotation axis is in the plane. Now we have to rotate by 90 degree. So 90 degree rotation makes in here, but 90 degree rotation now goes to the down pole. Now it goes to the down pole. This is 90 degree rotation makes upper pole. Another 90 degree makes down pole, and upper pole. Can you follow it? And this one makes upper pole, 90 degree rotation, goes back now another 45 and 45. So it makes down pole in here, it makes down pole in here. And it makes upper pole and down pole here, down pole here. Now, what I'll do is I do this threefold rotation operation. So it's in here, you should make one pole, upper pole, and down pole in here, so that this one makes threefold rotation operations. Again, the same thing. So there's a upper pole, down pole, there is upper pole and down pole, and there is a upper pole and down pole in here by these threefold symmetry operations. Okay. Now you don't have to do this set of twofold symmetry operation. If you do it, you know that it's already in there. So multiple rotation operation has been done by so far. Now you see that how many poles are generated. Now there is a 24 multiplication. It generates 24 poles by these symmetry elements. Okay, now with this, so far this is basic rotational symmetry, mirror plane symmetry, inversion symmetry, now rotor inversion symmetry. Now I discussed about multi-rotation systems of 2, 2, 2, 3, 2, 2, 4, 2, 2, 6, 2, 2, 2, 3, 3, 4, 3, 2. Okay, those are basic symmetry elements. Now, based on these symmetry elements, now we try to systematically derive the crystal structures in the sense of having these lattice point arrangements. So repetitiveness and symmetry are basic ingredients to generate all these crystallography elements. And if we do that, we can generate 7 crystal systems, and we can generate 14 Brava lattices, and we can generate 32 point groups. This 32 point group is all the possible symmetry elements along each lattice point. Now also we can derive 230 space groups, but in this lecture I will go up to the derivation of 32 point groups.